Good evening. I'll invite you to take a seat if you haven't already, and we'll get started in just a moment. Thank you. Thank you for coming. Well, we welcome you. It's so good to have you with us tonight for our 9th annual the Elving Anderson Lecture in Science and Religion. My name is Casey Shalapsky, and I'm the program manager for Ansem House. So Ansem House has been present on the campus of the University of Minnesota since 1982, and our mission is to connect the Christian faith with all areas of learning at the university. And we do this because we humbly contend that when we properly align faith and reason, the result is an approach to God, to our neighbors, to ourselves, and to the world that yields goodness, truth, and beauty. And so we sponsor events and nurture a community conducive to this end. So whether you're joining us for the first time tonight or have been a part of the Ansem House community for years, whatever perspective or background you bring to tonight's topic, we're delighted to have you with us this evening and for this conversation. I would love to make you all aware that Ansem House is settling into our brand new home, Melrose Station, which you can actually see out that window right across Washington Avenue. We're so happy to be here on the Minneapolis campus, and our new home offers a generous space for us to enact our mission, and we hope that after this lecture you'll join us for a reception where you can see firsthand the study center space, enjoy some refreshments, and continue the conversation. I'll have a few more details about that reception at the end of this lecture. So while we're settling into our new physical home, we're also creating a new institutional home for our academic engagement programs, a Center for Faith and Learning within Ansem House. The Center for Faith and Learning's particular focus within the broader Ansem House mission of connecting faith and knowledge with all of life is to support the University of Minnesota academic community in asking the big questions of ultimate meaning and purpose. Within that conversation, our center also makes available the intellectual resources of the Christian faith to the many academic disciplines and research communities present here. The center will function as a convener of important disciplinary and interdisciplinary conversations among faculty, academic staff, and graduate students. This evening, we continue a series of annual lectures focused on the relationship of the Christian faith to natural sciences. Our Anderson Lectures are named in honor of V. Elving Anderson, a distinguished geneticist here at the University of Minnesota, a committed Christian, a national leader in faith and science conversations, and a key early faculty leader of the McLaurin Institute, which later became Ansem House. We're delighted to have Dr. Carl Anderson, son of Elving and Carol, joining us for tonight's lecture. We thank you very much for coming, Carl. These Anderson Lectures have featured some of the most distinguished Christians in the sciences, speaking to the intersection of their faith with their academic work. Our past Anderson Lectures have included climate scientist Katherine Hayhoe, physicist Stephen Barr, geneticist Charmaine Royal, and Dennis Alexander, as well as many others. And for our 9th Anderson Lecture, we're delighted to host Brother Guy Consolmagno this evening on the topic, Captured by the Stars, Why Do We Look at the Heavens? And I welcome my colleague and director of the Center for Faith and Learning, Dr. A.J. Polarans, to introduce Brother Guy this evening. Thank you.
We're indeed very excited to welcome tonight Brother Guy Consolmagno, Director of the Vatican Observatory and President of the Vatican Observatory Foundation. And maybe I can say, like, personally, I'm very excited about it because I'm also an astronomer. And so it's great to have an astronomer come and talk to us here. Brother Guy obtained his Bachelor of Science and Master of Science in Earth and Planetary Sciences, both from the Massachusetts Institute of Technology, and his PhD in Planetary Science from the University of Arizona in 1987. He was on a postdoctoral fellow and a lecturer at the Harvard College Observatory and continued as postdoc and lecturer at MIT. In 1983, and he might actually talk about this a little bit. I don't know what he's going to talk tonight, but he left MIT to join the US Peace Corps, where he served for 2 years in Kenya, teaching physics and astronomy. And upon his return to the US, he served as an assistant professor of physics at Lafayette College, where he taught until his entry into the Jesuit order in 1989. He took vows as a Jesuit brother in 1991, studied philosophy, theology, and physics before his assignment to the Vatican Observatory in 1993. I hope I have all those dates correct. So far, so good? Oh, I missed one, okay. Where he also works as the curator of the Vatican meteorite collection, which is amazing. So the stones that fall out of the sky, and then you can find them then on the Earth. So the fireballs that you sometimes see, those are stones falling out of the sky, and they have like a really big value for research to figure out how the solar system actually works. And so looking at meteorites is actually looking into the solar system from the Earth, which is amazing. And the Vatican has actually a good collection there, and he's the curator of that. And then in 2015, he was appointed the director of the Vatican Observatory by Pope Francis. Brother Guy has co-authored and co-authored 2 astronomy books, a popular level book, Turn Left at Orion, which is a great book, and also a textbook in Planetary Science, Worlds Apart. He is also the author or co-author of 4 books exploring science and faith, including The Way to Dwelling of Light, Brother Astronomer, it's a great title. I think it's your biography, a little bit more telling about your own story, God's Mechanics, which is a little broader, and then Would You Baptize an Extraterrestrial? Which is the best title ever. He also authored several audiobooks, including Great Catholic Scientists, Discoveries and Lives of Faith, and Meaning, Exploring the Big Questions of the Cosmos with a Vatican Scientist. As an expert in small bodies in the solar system, which is kind of all the small stuff that is not planets and not dwarf planets, he of course also has an asteroid named after him. It's 4597 Consolmagno. It's in orbit around the Sun, which is great, with a period of 1,538 days. That is about 4 years and 4 months. So it takes a little to go around, a little longer than the Earth. So it's somewhere between Mars and Jupiter, where all the asteroids are. Not all of them, but most of them. How cool is that, right? His adventures have brought him all over the world, and he's full of great stories. And tonight's lecture is not only about astronomy, but also about the questions and the mysteries of deep space, and the way that we think about science and think about this reality and the religious roots of all our thinking. So before we start, I want to start with a brief prayer to pray for Brother Guy and to start our evening. Dear Heavenly Father, God of the universe, we pray for your blessing over this evening, and especially for Brother Guy. Strengthen him with your Spirit, and we pray this in Jesus' name. Amen. And please join me in welcoming Brother Guy Consolmagno.
Thank you so much. Yeah, he made me a little bit younger. I graduated in 78, not 87. Before I get into the topic itself, I know there are a lot of people who are curious about the Vatican Observatory. So I've got a very short video that gives you a little bit of the background that I'm coming from. And rather than having me stand up here and talk, I'll run the video because the guy who narrates the video does such a good job of it. How could I match him? Both science and religion are conversations about the universe. They're ways of learning how we interact with this universe. It's not simply a question of, is there a God, but there is a God, now what do we do? It's not just a question of, there are a bunch of stars, but rather, why are there stars? How do they work? How does that tell us how things work here on Earth? The interaction that I see in my own life is that religion gives me the reason to do the science.
Back in the papacy before Francis was Benedict, and one of his lines in a final elocution to the fathers of the general congregation was, "Go to the frontiers." Well, there isn't much more frontier than 3.7 billion years away.
The first official interest of the Church for astronomy started in 1582 with the reform of the calendar. Then in 1891, Pope Leo XIII wanted to have an observatory to show that the Church is not against science, but the Church promotes good science.
They start out by having telescopes on the Tower of the Winds, and then on the walls surrounding the Vatican, as the city lights grow, and as the Italian government gives them back the territory out in Castel Gandolfo. In the 30s, they build new telescopes on the roof of the Papal Palace in Castel Gandolfo. Best telescopes of their era in the 1930s. By the 1980s, light pollution makes those telescopes unusable, so we build a new telescope in the dark skies of Arizona.
I'm Father Jean-Baptiste Kikwaya Eluo. I'm working in 3 projects. The first one is NEOS, Near Earth Object. So what I'm doing with NEOS is just observe them using our modern telescope VAT. The second project is meteors. I worked on very faint meteors, what we call shooting stars. And the third project is set fireball network. They will have 4 cameras here around Tucson so that actually we can monitor any fireball getting into the Earth atmosphere in the region.
This telescope, the Vatican Advanced Technology Telescope, it was the first of the new technology telescopes that has been considered pretty much the norm now in developing telescopes. With the advance of computer technology, we have the capability of bringing that advanced technology directly into our telescope. So it's an expandable, it's almost like it's a living machine, so it can grow as technology grows.
It is still very important to maintain scientific research at the Vatican, simply because there is still a lot of confusion about this relationship between science and faith. We are not out here trying to prove the existence of God by looking through a telescope. That's not what we're doing. But we can say that if we want to obtain any reasonable results looking through that telescope, we need to do it embracing a certain work ethics that is, in fact, the same work ethics that the Bible itself tells us through commandments and through the Gospels to embrace.
Human beings look at the stars and wonder. They want to know, what is that? What is that about? How do I fit in? They hear about the moon landing and they want to know, what was that like? If we're part of the human race, we're part of the race that went to the moon. We're part of the species that looked at the stars and wondered, what the heck are those things? Looking at the sky reminds you that there's more to the universe than what's for lunch. What's more, if you believe in a universe that God so loved that he sent his son, then not only are you going to want to study the universe because it's kind of cool, it's an act of worship. It's an act of getting closer to the Creator and getting closer to a universe, as St. Athanasius said 1,500 years ago, was cleansed and quickened by the Incarnation. Then, doing science is an act of worship. Men of Galilee, Why do you stand here looking up at the sky? It's a line from the gospel, what the angels say to the disciples at the ascension. And by the way, it was also the theme of the first sermon preached against Galileo, a pun on the name Galileo in Galilee. And Galileo and his wild and useless ideas inspired by looking up at the sky with that newfangled telescope. It's both senses of looking at the heavens that I want to explore today. It's the big question for anybody who does science or art: why do we do it? What motivates us? Not only to choose it as a career, but to go into the lab or go into the studio day in and day out and put in the long hours of work. Now, there's this fun experiment that I do in my meteorite lab, and okay, I should explain. I am a meteoriticist. That means not that I take care of the weather, but I study meteorites. Meteorites are the rocks that fall from the sky. They give us free samples of the asteroids, sometimes even Mars or the moon. Once they fall, some of them get found, and once they get collected, with luck, some of them will wind up in our labs, and in that case, people like me, in principle, can study them. But actually, meteorite collectors are very different from the meteorite curators. The one in the Natural History in London is called the meteorite keeper. And the argument is that he keeps the meteorites and doesn't let anybody else touch them, which is tough to do when you want to do experiments on them, except when I arrived at the Vatican Observatory, which was about 30 years ago, there was no curator of the meteorites, so I appointed myself the curator and gave myself permission to do the experiments. Why do we have meteorites? The collection was assembled in the 19th century by a wealthy French marquis, the Marquis de Maurois, I think it's pronounced. At least that's how you'd say his name if he was a hockey player who played a goalie. It's a collector's collection, which means as a collector, he wanted a little bit of everything. And that meant that it's ideal if you're going to survey the properties, the same sort of property, like, say, density, over all the different types of meteorites. And that's what we wound up doing. We're measuring density and porosity, magnetic properties, thermal properties. Just as an example, one of the things I'm interested in measuring is the heat capacity, which is the capacity of the rock to hold heat. How much heat does it take to raise the temperature of the rock by 1 degree? How much heat comes off when the rock drops by 1 degree? So, how do you measure that? Actually, there are these million-dollar machines that can do that really precisely, and as it happens, a buddy of mine at Boston College, Cy Peel, who also is a Jesuit priest, happens to have one of these machines. You take a little piece, you put it in that very tiny container that's about a couple of millimeters across, you put it in the gizmo, it step by step by step takes you from room temperature down to a couple of degrees above absolute zero, making the measurement every step along the way. And when it works, because they're really tricky to work, because they've got to be calibrated all the time, and they have to be fixed half the time, but when they work, boy, do you get gorgeous data. I don't have that kind of money. I don't have $1 million. I don't have a full-time technician. I don't have enough nights to go through measuring every meteorite in the collection that way. And for that matter, if you measure just a tiny piece of a meteorite, how do you know you got a representative sample? Because meteorites are notoriously different from one place to the next to the next. And beyond that, even though I do like to make, experiments, I don't want to carve up every meteorite in my collection. So, how can I make this measurement on the whole rock without actually carving up the meteorite? I was talking about this with a colleague of mine from France, and he came up with a clever idea. He doesn't remember coming up with it, but I know it was his idea. Here's the idea. You take a doer, which is an insulated container, like that sippy cup there that has a Buzz Lightyear on the side. You fill it with liquid nitrogen, you put it on a scale, you hook the scale up to a computer, and then second by second you measure how the weight slowly drops as the nitrogen boils away. And then you drop in the meteorite. The weight goes up, of course, But because the meteorite is hot, the nitrogen starts boiling and boiling and boiling until all of that extra nitrogen is boiled away. That's the difference. That tells you how much nitrogen was due to the heat in the rock, and you know how much heat it takes to boil away 1 gram of nitrogen, and that tells you how much heat there was in the rock released when it went from room temperature to liquid nitrogen temperature. It's really cool. Where do you get doers? Actually, we didn't use the sippy cup. We went to Target and bought ourselves a thermos, coffee thermos. Where do you get liquid nitrogen? It happens that we are located in the Pope's Summer Gardens right next to the dairy farm. As they said, dalle stalle alla stalle, from the stalls to the stars. And if you know anything about farming, I guess there are probably a few people who came from farms here, you know in order to get milk from a cow, the cow's got to have a calf. In order to have that, the cow has to have a bull. So no jokes about papal bulls, please. In fact, what they use is frozen bull semen, which they freeze using liquid nitrogen. So they've got a big tank of liquid nitrogen, and every time we need one for our lab, we go over with the doer and borrow a cup of nitrogen. It's great. Naturally, it's not that easy. There's all sorts of little effects that you have to worry about. For instance, when you have the nitrogen out in the air, water vapor will freeze on top of the nitrogen, and that changes the weight. So you'll see my little doer sitting on the scale there. It's on a cardboard box, because if the doer gets cold, then the scale gets cold, and that changes the way it measures the weight. So we've got that. And then we've got this plastic thing over it. It looks like a big plastic cylinder. That's a gizmo I bought at a €1 shop in Albano, the town next to us, that was designed to hold dry spaghetti. Fits over it perfectly. And the nitrogen fills it, drives away the water-rich air, and then we can make our measurements. And there's also this fear that if you drop a rock into liquid nitrogen, maybe that's not so good for the rock. You probably know about liquid nitrogen. You've seen the demonstrations where you put a flower or a banana into the liquid nitrogen, and then it freezes, and then you hit it, and it shatters. It turns out, every meteoriticist knows, that iron meteorites are really hard to break, because they're made out of iron. And the easiest way to do it is to drop them in liquid nitrogen. So isn't that dangerous to put my rocks in liquid nitrogen? I looked it up. That's how you do it. You take the iron meteorite, you drop it in the liquid nitrogen, you get it really cold, and then you hit it with a sledgehammer. So as long as I don't have any sledgehammers out to tempt people, I'm okay. It's not going to break anything. Now, over the past 10 years, my colleague Bob Mackey and I, Brother Bob, he's the curator of the meteorite collection, now that I'm the director. And we've gotten some great results, and I could tell you about these results for the next hour, but that's not why you came here. What I really want to talk about is something bigger, which is, why do we do these experiments? I mean, who cares? Heat capacity of meteorites? Yeah. Nobody's ever measured that before, maybe for the reason that, nobody could find a good reason to measure it before. Actually, we've discovered now that we've had the measurements that other scientists are using our numbers when they try to make models to explain how asteroids heat up and cool off. But then, why do we care about asteroids? Well, actually, it's possible that the numbers we come up with will help us to plan how to mine an asteroid for its mineral wealth, or deflect it if it's going to come and, destroy all life on Earth. And actually, that's true. The numbers we have measured are really useful in trying to figure out how to deflect asteroids, or how to control asteroids, or how to mine asteroids. But that's actually not what gets me up in the morning on a Thursday morning and go down into the lab and drop a few more meteorites into the liquid nitrogen and start making the measurements and go into the computer and analyze the data. It's not like I'm thinking in the back of my head, I've got to get these measurements or else 25 years from now, you know, the human race will be toast because we didn't know how to deflect the asteroid. That's not what's going through my head. So what is going through my head? Why do I do it? There's actually two parts to that question. Why does society support me to do the science? You could say, why does the church support me? But then, you know, why does the government support my colleagues? Supported me before I was a Jesuit. And the other question, what motivates me personally to decide that this is what I wanted to do? Because yet to do science, any kind of science, requires money and time and talent, and all of those are in as short supply as meteorites. Science only happens when somebody is convinced that the science itself is worth doing, and it's worth the cost in time and personnel and money. And that's something you can't take for granted, as we find when we try to get money out of the granting agencies. It means that the scientific questions that get answered are the ones that somebody decided were worth answering. How is that decided? When it's done right, and this is kind of what we do in the astronomy field nowadays, all the astronomers get together once every 10 years, we take a big survey of what people think is important, we come up with a list of priorities, we write a big white paper, and that goes to NASA and it goes to Congress, and with luck, they'll say, okay, these are the missions, these are the questions that the astronomers think the most resources should go to. When it's done wrong, which is how it happened before we did that, well, it's a fight over whose university has the most powerful Congress critter. Who's going to pull rank and force the passage of some nice nugget of money that will go to an institution in their congressional district. The probe to Pluto that took that nice picture of Pluto there, that was a $1 billion earmark pushed through by the senator from Maryland because the money was going to the Johns Hopkins University in Baltimore. And incidentally, it's no surprise that the Hubble Space Telescope and the James Webb Space Telescope are run by the Space Telescope Institute, also in Baltimore. Funny how that works. No surprise that the Johnson Space Center was put in Houston when Lyndon Johnson was the vice president and had power about where the money was going to go. It was such a power play that our field finally said never again, and that's when we decided to do these white papers. The idea of going to Pluto was a real long shot, and it was a probe that actually a lot of us argued might not come up with any interesting results. It did come up with interesting results. Good for them. We got some good science out of it. But the fact that they got the money means that some other probe to some other destination didn't get the money, never flew. We don't know what it was that we didn't discover as a result. Instead of those pretty harp-shaped thingies that you see on Pluto, we could have gone to Europa, looked for the oceans of Europa, and even looked for life and evidence of life in the oceans of Europa. Just this past week, the Europeans have launched a mission to do exactly that. And it will come up with some good answers by the time I'm about 80 years old. Whatever it finds, we could have found out 20 years ago, when it wasn't quite so old for me. But the cost of doing science is more than just the money. 20-odd years ago, I gave a talk at the College of Charleston, which is this beautiful campus in Charleston, South Carolina. And after the talk, an undergraduate came up to me, and he's full of enthusiasm, and I was talking about the moons of Jupiter and the geology you could do there. And he goes, wow, I want to be a geologist. And I'm going, that's great. My undergraduate degree in Earth and planetary law, that's geology of other planets. It's a fun field. It's full of great people. There's all sorts of wonderful stuff you can do. And if you choose the right corner of it, you can, wind up working outdoors in some of the most beautiful places on Earth. So, you want to be a geologist? I say, sounds good to me. And then he goes, well, yeah, but what do I tell my mom? South Carolina, Bible Belt. in the culture where he grew up, studying geology with our idea that there are billion-year-old rocks in a 4-billion-year-old Earth, would be directly contradicting the religion that he'd been taught. To be a geologist, for him, would be like declaring war against his religion, his home, his family. His mom would be ashamed of him. Scientists are people. We've got families, we've got desires. Like every human being, we're a mixture of reason and heart, where hearts have reasons that reason doesn't know. And like that student, we have to answer the desires in us, and those desires inside the people who are very close to us. Now, there's this temptation to divide our experience into separate categories: faith versus science, emotions versus logic. It's a false division. Real people are not just Kirk or just Spock. For that matter, neither were Kirk or Spock, but that's a whole different conversation. Because it's on the basis of both reason and gut feeling that we make all the decisions in our life. You know, in the case of the student from South Carolina, he's got to choose between what he wants, what he thinks his family and his community want. Now, I do get asked about science and religion all the time, comes with the job. And I have a hard time sometimes talking to people about the divide because I've never experienced the divide and I don't know what they're talking about. It was the nuns who taught me science back in the 60s. I've never felt uncomfortable. Why do people feel that way? I got a great insight, actually, one day when I was talking to Captain Kirk. How I wound up meeting William Shatner, well, okay, long story. But I mentioned I was a Jesuit scientist, and he was flabbergasted. Wait a minute, I can hear him say. And we talked, and suddenly, he got through to me something that was so obvious to him that I had never grasped before. He saw science and religion as two competing sets of truth, two big books of facts. And what's going to happen if there's a fact in one book that contradicts a fact in the other book? Of course, if you do think that science is a big book of facts, you can imagine that. If you do think that religion is a big book of facts, I can see how that. But science is not a big book of facts. Let me give you an example. The orbits of the planets are facts. Now, you can describe them by Ptolemy's epicycles, circles within circles within circles. You can describe any possible orbit if you have enough epicycle circles. You can go on internet and a guy has worked out enough circles within circles within circles to draw out a figure of Homer Simpson. If ever there was a planet that orbited like Homer Simpson, Ptolemy would be able to describe it. Kepler's ellipses are only approximately true. They don't actually account how one planet pulls on another planet, just how the sun pulls on the planet. So, which is the better description of the orbit? It's actually Kepler, even though it gets it a little bit wrong, because it's only Kepler's ellipses that lead to the insight of Newton's law of gravity. Science isn't the facts of the orbits, it's what you do with the facts. And it's also being open to realizing that Newton's law of gravity, which is pretty darn good, isn't the last word. Not even Einstein's general relativity is going to be the last word. Who knows in the year 3023 what people are going to be saying. Furthermore, science is not this collection of, worrying about one fact. I have never, in my experience, had something in my religion that seemed to be contradicted by something in my science, because they're not really talking about the same stuff. But I have found one thing in my science which was contradicted by a different thing in my science. And when that happens, I jump for joy because I'm about to learn something new. And I'm going to get a paper out of it, and who knows, maybe fame and glory. For that matter, our faith also is not based on rigid certainties. I was talking to William Shatner. I used this phrase that I had read in a book by Anne Lamott, who describes faith this way. She goes, the opposite of faith is not doubt. The opposite of faith is certainty. If you're certain, then you don't need faith. It's when you're not certain, but you have to make a decision anyway. That was completely opposite to what William Shatner was thinking about. He had heard that phrase, blind faith, and he thought that blind faith meant, accepting something as certain without looking, or better yet, putting a blindfold on and refusing to look. But that's not Scripture. Remember what Moses says to his people after giving them the tablets of the law. He says, do not forget the things your eyes have seen, or let them fade from your heart as long as you live, and teach them to your children and to their children. It's not close your eyes. It's rather teach what you have seen. Every religious experience starts with an experience. Blind faith isn't walking around with blindfolds. Blind faith is proceeding after you've done everything you can see and still realizing you don't have enough data to make a decision perfectly, and yet you still have to make the decision. If we knew the answer, we wouldn't need faith. Certainty is the opposite of faith, but we don't know that. We never have all the facts. Faith is how we deal with the fact that we have to keep moving even when we don't have all the facts. Decisions that we make, like, where am I going to go to school? I made a mistake. I transferred schools. Decisions like, who am I going to marry? Where am I going to live? What job am I going to take? You don't know ahead of time how it's going to turn out. You have to proceed on faith anyway. My student friend in the College of Charleston, maybe he's going to choose geology, maybe he's not going to choose geology. But it will be an act of faith, not because he found the answer in the Bible or that he was able to calculate it without a slide rule, but because he couldn't find the answer there and he had to follow the tugs of both his head and his heart. All of life is making decisions based on inadequate information. It's a leap of faith to start a family or to join a religious community. And what's worse, these decisions that control our lives are not only based on inadequate data, they're made by ignorant, stupid, and inexperienced teenagers, namely us. That was me before I had a beard. I was a goofy teenager back then. When I was 18, went off to the university, I had no idea what I wanted to do. I grew up in Detroit, but I wanted to go back east because my dad was from Boston. Went to Boston College because I'd been to a Jesuit high school. I thought, maybe I'm going to be a Jesuit, who knows? At Boston College, I had this idea, maybe I'll be a Jesuit priest. When it came time to declare a major, I wanted to check the box that said all of the above. I wasn't quite sure where I wanted to go. So, how did I wind up doing planetary sciences at MIT? Well, I started out as a history major at Boston College, but I didn't fit into the dorms very well. They're guys who just wanted to party, and I was a nerd. And my best friend from high school was at MIT, big nerd school, full of nerds just like me, and they had weekend movies, and pinball machines, and tunnels you could explore at night, and the world's largest collection of science fiction books. I figure if I'm going to be a nerd, I ought to go to nerd school. So I transferred, and they accepted me. And when I got there, I was happy like I couldn't believe. This is where I was meant to be. This is what I was good at. This is what I loved. This is where I could stoke my passion. And it turns out it wasn't the science fiction, it was actually the science. It wasn't just the tunnels, it was the exploration. It wasn't the movies, it was the imagination. And it wasn't just the work, it was being part of a community of fellow nerds. Even though I did feel like an imposter, it turns out everybody in physics feels like an imposter. I would venture for every Harry Potter fan who wants to do magic, there are a dozen who just want to go to Hogwarts and know what school, class they're sorted into. I remember reading Lord of the Rings, and I wanted to be part of a great fellowship. And that's what science is, sharing stories about what we've learned about the natural world. And to share stories, you've got to have a community of people to share the stories with. And if without a community that's interested in the stories, you don't have anybody to tell it to. And it's not just stories about where you want to go to school, but nobody wants to hear about your stories of what happened in the lab. If that's the case, then you're going to stop going to the lab. Science is done as part of a big community. If you don't have the community supporting you, it's not going to happen. It can't happen. There's nobody there to teach you how to do the science. There's nobody there to hire you to teach the next generation about how to do science. Think about this. There's a lot of mountains in India. Heard of the Himalayas? There are more people who live in India than in Switzerland or Norway or Colorado or, frankly, all of the US and Europe combined. How many skiers from India have won medals in the Winter Olympics? 0. Sports of that sort at that level just aren't supported by the Indian society. For whatever reason, there are not very many mothers in India who dream of their daughter winning the gold medal in figure skating. And if the society that you live in doesn't think that doing science is part of the thing that will make a mom proud, you're not going to find very many kids who choose to do science or to persevere in the study. You won't find anybody who can teach you how to do it. Next time you worry about underrepresented minorities in your field, remember what kind of background they're coming from. Are you giving them something that their moms can be proud of them doing? When I was in grad school, I had a friend, fellow grad student, who was from a poor neighborhood in Buffalo. And when he hit, the brick wall that you always hit when you suddenly wonder, maybe I'm not good enough, maybe I can't do this, maybe I should quit. He called home and his mom would say, come home, Cliff, you could repair TVs in Buffalo and make a good living. Which is not what actually, I think that probably motivated him to stay in graduate school. He did get his PhD. Incidentally, while we're talking about India, ancient India was so far ahead of the rest of the world when it came to mathematics. What we call Arabic numbers were actually not Arabic, they're an Indian invention. But they didn't invent the study of the natural universe the way that, the medieval universities in Europe did. For the Chinese, the highest achievement was to be a person of culture and ethical behavior. Just like the Manichaeans in ancient Rome, the physical universe was a source of temptation. Chocolate is designed to make you fat and give you acne. You find echoes of that even in scripture in places. But the people of the book, the Jews, the Christians, the Muslims, we also have a belief that this physical universe was created by God, who looked at it in each stage of creation and declared it was good. Chocolate is a foretaste of the joy of heaven. It's a sacramental. Should be celebrated as such. God reveals himself in the things that have been created. That's not me saying that, that's St. Paul in the first letter to the Romans. We believe in a God that so loved the world, not good people, not nice ideas, not ethics, but the world, so much that he sent his son to redeem this world. That kind of argument affects the choices that a society makes about studying the universe or not studying the universe. So why do we do it? Similar moral ideas, dare I say, religious ideas, affect the choices of us as individuals. Why does any particular person decide to be a scientist? What goodies does being a scientist give you that no other career could give you? Being a scientist lets you do what? What are we trying to do? What constitutes success? When I was much younger, I joined the U.S. Peace Corps. I was one of a group of 80 teachers, most of them right out of college, full of idealism. We had a month of training stateside before we went off to Africa. And in between the breaks of teacher training in Swahili, we used to play this game called Hacky Sack. Let me see if I can go back again. Right. The idea is somebody tosses a beanbag up in the air, And then you try to keep it up in the air as you pass it back and forth, kicking it or bopping it or doing whatever you want to do. It's a kind of feel-good, cooperative kind of games that Peace Corps volunteers would like. During training, one of the women from New York had her boyfriend come out and visit. And he's from New York, and he's looking at this, and he goes, "I don't get it. How do you win this game? Do you like knock down the other person so they can't?" No. You do grab it? No. You just kick it up in the air? There's no goals? There's no contact? How do you win this game of science? Science is like hacky sack. It's this cooperative activity. You gain status by how much you give, how much you add to the field, how much your work helps the other people in the field. You try to keep all these ideas up in the air, keep them alive, pass them to the next player. There's never a moment when you say, "I won, you lost." So what's your goal? How do you win the game? And this is, PhD comics. It's been 45 years since I was a PhD student, but nothing has changed. At first you say, "I want to win a prize," at least I want to get a job, at least I hope they have pepperoni pizza at the colloquium. There are lots of obvious criteria for what a university might consider signs of success. The approval of others, because you get good letters of recommendation, tenure, grant money, prizes, the MacArthur Fellowship, the Nobel Prize, fame in general, getting your name in the New York Times or Sky and Telescope. Another sign of success is having successful students, like parenthood. You may be tempted to live through your offspring. And then there's, of course, the favorite metric of tenure committees: have your papers been papers that other people have used? The more papers, the more citations, the more successful. But is that why we do it? There's another carrot that gets people to work hard in academia. In other words, if you're successful, you might reach a state where you can set the criteria for what you want to study, what the rest of the field wants to study. You're on one of those committees that writes the white papers that tells NASA what we're going to do for the next 10 years. But all of these are kind of circular arguments. The prize for doing science is you get to do science. That can't be the whole story. Here's a table of contents of Science Magazine, one of the top scientific journals in the world. Getting a paper published in Science is a big deal. That's a sign of success. Do you wake up in the morning and jump out of bed and rush to the lab because, by golly, you're going to be one of the et al. Authors that's going to tell the world something really exciting and groundbreaking about the effect of collective molecular reorientations and Brownian motions of colloids in pneumatic liquid crystals? It's good work. It's cited 20 times in the next 3 years. Is that what motivates you? What are the personal motivations that make you want to do the work? Maybe you're just curious and you love following your curiosity. Maybe you just get a kick out of solving problems, finding patterns. That's the same thing that makes jigsaw puzzles fun, crossword puzzles fun. But science has got to be more than just, a giant crossword puzzle. And as we saw with that student in South Carolina, the approval of family and friends plays a big role. Maybe I want to be a scientist because then everybody will think I'm smart and I'll get a pat on the head. What about love? If we didn't love the work, would we keep doing it? After 4 years of undergraduate and 4 years and 6 years and 8 years of graduate school and postdoctum, it might be the only job you know how to do. Is that why you're doing it? Is that why you make it the center of your life? How do these criteria stack up against the first set? Which candidate would your committee choose if you were trying to choose somebody to add to the faculty of your department? Are you going to have the faculty member who really loves the material or the one who publishes the most papers? And let's be honest, which one actually is going to make the better scientist for your department? But in real life, it's never such a clean choice. Would you sacrifice anything on list 2 to avoid losing anything on list 1? Would you give up the approval of others to satisfy your own curiosity? Or vice versa? Would you give up tenure to satisfy the approval from your family, or vice versa? Would you give up academic freedom, the freedom to pursue your own research in order to be able to have the pleasure of solving problems? In other words, I can be in academia and choose my own topic, but I'm not going to get very well funded, or I can go to industry and have a heck of a fun time in a really well-appointed sandbox doing the work that somebody else wants me to do. How do you make that choice? Do you give up fame in order to satisfy finding patterns, or vice versa? Do you give up grant money in order to search for the truth, or vice versa? Where is your heart? Where is your God? And what does that say about the sort of God you worship? Why are we doing this? What does winning look like? Why do we as individuals choose to do the science? What are we looking for? How do we know when we've found it? Internal satisfaction is important, but it's not enough. If you don't have something to give to the community, what is the ultimate criterion? Is it truth? What is it? Is it, if you lose sight of whatever the criterion is that got you into the field in the first place, then the work becomes meaningless, and you do a bad job of it, and then you don't get to do it anymore. But if you didn't have that internal motivation, you wouldn't be doing the work for very long. About 2020, 06, 07, I did a sabbatical year at Fordham University, Jesuit school in New York City. I had a class of really, really bright students, and I asked if I could teach the introductory class on electricity and magnetism, and I wore that t-shirt, and God said in all of these crazy equations, and there was light. And I said, by the end of the term, you'll know what all the equations mean, and you'll get the joke. So, 2/3 of the way into the term, I'm writing Maxwell's equations, these things. I'm writing on the board, and I'm doing the mathematical manipulations that Maxwell did back in 1865. You know, how the equation for electricity gives rise to magnetism, how magnetic fields can give rise to electric fields. And then you take a derivative here, and you put a substitution there, and as I'm writing down the final equation, the result of all this manipulation, complicated scrawls of e's and t's and del's and mu sub zeros, before I had a chance to turn to the class and show what it meant, the brightest student in the front row looks at the second-order differential equation with respect to time equal to a second-order differential with respect to space with a bunch of terms, and he goes, "Oh my God, it's a wave." And it is. That's what Maxwell came up with. Maxwell showed that light and radio and everything in the electromagnetic spectrum could be described by the equations that they had at the time. And out of this, not only radio and television, but spectroscopy, and ultimately quantum theory and relativity came out of those equations on my t-shirt. It really was an oh my God moment. But what accompanied it was this enormous burst of joy in the student who saw it, and in the joy that I remembered having, which is why I wanted to teach that class, so that I could introduce students to this wonderful joy. Let me show you joy. These are images from our telescope in Arizona. Galaxies, planetary nebula from gases exploding off a star, supernova remnants, galaxies with dust clouds, another planetary nebula where the red shows you where the hydrogen is, and the green where the oxygen is. Dust clouds that are not only telling you really cool things about the science happening there, but also look really cool because they look like a little horsey. remarkable colors. You can see why we can be captivated by stars. It doesn't take a PhD to want to go outside and look at the night sky. But let me tell you, if you've got the PhD and the science behind it, it's just a whole new dimension of cool. When you see these things and you go, oh, did you see? And then there's my own field of meteoritics. Going from light years to, fraction of a millimeter, polarized light. There's good science in those colors, but there's also beauty. Every bit of science we can extract from these pictures starts with Maxwell's equations and the fact that, oh my God, it's a wave. The fact that it's a wave gives us radio and electricity and power transmission. Now, in my own research, I've never had as big an oh my God moment as I'm sure Maxwell had, but I've had enough small ones, enough to get published in Science. But it's not the paper that got published in Science that I remember. It's the grasp of amazement when I suddenly saw a pattern in nature that I had not anticipated. Let me end with one Peace Corps story. The whole reason I went to Africa with the Peace Corps was precisely because I had lost that sense of joy. I was a postdoctoral fellow at MIT, the big leagues. I was a third-string utility infielder, but I was in the big leagues. But it wasn't enough. I'd forgotten why I wanted to do the science. I was pushing 30 years old. This is my 5th year of postdoctum, which meant I couldn't get a job. I had forgotten why I wanted to do science. I'd have to walk across that bridge every day to have my office in that skyscraper there, the green building at MIT. And it was a long walk, especially in the winter. And at night, I'd be back in my apartment in the South End, staring at the ceiling and wondering, at 3 a.m., why am I worried about, doing science with meteorites when there's people starving in the world? And I didn't have an answer. So I quit. I left my position at MIT. I joined the Peace Corps. I said, I'll go anywhere you want me to go. I'll do anything you ask me to do. And they asked me to go to Kenya and teach high school and live in a mud hut and teach in a classroom where there was no glass in the windows and no black in the blackboards. And I said, yeah, I'm going to do something worthwhile. As soon as I actually got to Kenya, they discovered I had a doctorate, and they said, okay, maybe not a rural school, maybe a government school, maybe a national school, maybe the best high school in the country, the Starehe Boys Center, where we had an astronomy club, and these kids were showing off their little space stations to President Daniel Arap Moi, the president of Kenya, who came to visit. And I was there 2 semesters, and they moved me to the University of Nairobi, where I wound up teaching graduate students astrophysics, which I could have done back in Boston. Now, there was a logic. The guys I was teaching were all had jobs waiting for them at the Kenya Science Teachers College. I was teaching the guys who'd be teaching the teachers who would, okay, that made sense. But that wasn't why they wanted to learn astronomy. Because every weekend, you see, I'd go up country out of Nairobi, visit my friends from the other 80 teachers who were in the real Peace Corps with the mud huts and all of that. And I took a slide tray of, astronomical images, NASA images, a little telescope. I talked to the schools. That was me talking to a school when I was very, very skinny. You want to lose weight, dysentery is remarkable. And everywhere I went, the room was packed. They wanted to hear what NASA was discovering. And every time I set up the telescope, everybody in town wanted to look at it. The moons of Jupiter. And they'd go, wow. The craters on the moon. And they'd go, wow. And they would go, wow, just like my friends back in Michigan, in the Thumb area where I was, growing up. How many people here have ever seen Saturn and its rings through a small telescope? Okay, how many of you guys have ever seen Saturn and its rings through a small telescope and not gone, oh, wow? That's something that ties all of us together. Back then, I had a very clever cat. The cat was much better at being a cat than I could have been. But the cat had no interest in looking through the telescope. Telescopes are for human beings, looking at the stars and going, ah, and wondering, what are they? And who are we? And how does it all fit together? And how can I be part of this conversation? That's what makes us human. That's what makes us more than just, well-fed cows. To deny that to somebody denies them their humanity, to make it available to people, to remind them that we are the species that have gone to the moon, us, the whole human race, not just the astronauts, but the people who built the rocket, and the people who figured out how to pay for building the rocket, and the people who fed the people who built the rocket. It's human to look at the stars and to realize that there's more to life than what's for lunch. The very thing that makes us different from a clever cat, the very thing that makes us breathe out, oh my God, that's the human soul, the image and likeness of God. And so, every morning, I look forward to going back to the lab, dropping meteorites into liquid nitrogen, finding out how each new number falls in the plot of the data. It's slow and it's tedious, and it's fun as all get out. I mean, meteorites, right? You can touch pieces of outer space. And liquid nitrogen, what's more fun than that? And every now and then you see a plot like this and you go, wait a minute. Everything ought to be on the line, but instead they're above the line. That's telling me something. What is it telling me? I don't know. But my science needs that. All science needs that. Science only happens because of the oh my God moments. Science needs oh my God. Nothing would happen without it. And that's why we will get support from the church, from a pope who himself was a chemist. I mean, look, he showed up in my lab wearing a white lab coat. And that's why at the end of the day, it's important to remember, creation occurred over 7 days. The first 6, day by day by day, all the physical pieces were put together. But the climax of the story of creation is the Sabbath, where we spend the time to admire what God has done. And if you lose that, then you've lost the reason for why you're doing the science. Thanks a whole lot for coming.
Thank you so much, Brother Guy, for this inspiring and deeply thoughtful lecture. This was amazing. Thank you so much. We have some time for Q&A, and so there will be 2 microphones that will be run through the aisles right here. When you ask a question, I want to ask you to be brief and concise. Sometimes some people have a tendency to give their own lecture when they ask a question. So I want to ask you to be brief and concise so that we can go through as many questions as possible. And only ask a question when you have a microphone in your hands, and then also speak in the microphone so that everyone can hear it. Yeah, so those are a couple of the ground rules. So if you have a question, raise your hand, and I'll point out, and then you will get a microphone. And only when you have a microphone you can start speaking. Yeah.
Microphone person.
Looking back at your observational history, all astronomers have deep inside a memory that can be described best as your best night ever at a telescope. What's yours?
I'm both an amateur and a professional. Just like somebody who might be the captain of an oil tanker likes to go dinghy sailing on his day off. And I had this joy of going to Antarctica searching for meteorites back in 1996. And afterwards, I was going through New Zealand and had a night outside of Lake Tekapo in the South Island, looking at the southern sky. And it was crystal clear. And my friend of mine had put together a list of cool things to see in the southern sky with a small telescope. And I'm checking them all off, and I'm looking at the Milky Way. And there was a knot of light that I knew, I'll bet you that's something in the telescope. It's not on the list. So I went and it turns out my friend goes, oh my gosh, I forgot to tell you that one, that's the best. It was the Eta Carina complex. And it's like, if you've ever seen Orion, it's like Orion on steroids. It just keeps going and going and going. And the longer you look, the more you see. Wow. That was God shaking my hand and saying, you see the cool things I do?
Just a quick piece of trivia. Do you do most of your work at Castle Gandolfo in Italy or in Mount Graham up in Tucson?
I'm a meteoriticist, and so the meteorite collection is in Castle Gandolfo. So that's where I do that work. However, for about 20 years, I had a collaboration with a fellow named Bill Romanishin, who was a professor at the University of Oklahoma, and Steve Tegler, who was a professor at Northern Arizona. And we were interested in the colors of the trans-Neptunian objects. And the idea was just take a survey of what's out there. So our telescope was ideal for that because it was a fishing expedition. We had no idea if we'd see anything. We're not going to get time on a big telescope. Well, we can see enough of these 21st magnitude things with our telescope, just in red, green, and blue. Do you see anything? So for about 10, 15 years, I'd go back to Arizona at a time when we had telescope time and help them out doing the observations. What we found was really cool, that they come in two distinct colors. Either they're colorless, gray, or they're very, very red. And the colors are related to the way they orbit, whether they've got nice circular orbits or whether their orbits have been pumped up. And now other people with bigger telescopes have gone and surveyed twice as many as we ever did. But we made the original discovery on that telescope. Most scientists, you'll find, will have 2 or 3 different projects going at any given time, because you never know if one of them is going to turn out to work or not. So you want to have more than one in case the one you were working on turns out to be a dead end.
Oh. Can you stand up so we can actually see you where you're standing?
Yeah.
Hello. Hi. I was wondering if you have a favorite meteorite and what it is about it that makes it your favorite to study or talk about.
It's like asking a mom if they have a favorite child. But that one that I showed you the picture of, Kinyahinya, I just love that picture. I took it totally by accident and just, wow, that's cool. I could go back and show it to you because we used it as a Christmas card one year. Do you see the little baby? So just for the sheer beauty of it, I love that meteorite. There are other meteorites with a lot more exciting science behind them, but that's one that just tickles me.
As a non-scientist, I was going to shift to a spiritual question, maybe words and semantics. Vocation, and you seem to double up on it. And can you offer some observations on vocations?
If my Latin is not too awful, I think a great English version of that is calling, voca, is to call. What is... Part of me, especially when I was younger, was that God has given me free will, I can do whatever I want, and as long as I do a good thing, God will be happy with me. And then I discovered there are some things that God really liked me to do. And there are places he really wanted me to be. And he would make his displeasure very, very clear if I was trying to go someplace else, because I'd be miserable at it. But everybody's vocation is different. And the difference to me was whether or not I was content. I was always happy. I was always a happy person. Even when I was doing stupid things, I'd be happy. But was when I entered the Jesuits that I had this, okay, this is where I was supposed to be. Not as a priest. I would make a terrible priest because, I'm a nerd. But I make an okay brother. And being a nerd for Jesus is, the best kind of nerd, right? But the calling is to be the nerd, because everything ought to be for Jesus. So the real vocation is to find your particular nerddom. And it will take a long time. Don't expect to know it when you're 18 or 22 or 24. Took me till I was nearly 40. That's okay. I had a lot of fun in the meanwhile. Yeah, esatto.
Hi. I think you touched on where I was going with my question a little bit already here, but I noticed you have such a childlikeness to you, is how I would describe it, like a childlike...
Immature, I think is the
No,
word.
no.
people use.
The flip side of it is a beautiful childlikeness to what you do and to what you love and in your work. And I wonder if you have anything to say about why you can have that at this advanced age, and why...
well,
and why perhaps, if you have any thoughts on why that goes away, in so many grown-ups in this day.
I remember really well being a kid. I had, an incredibly happy childhood. I had everything going for me. I had parents who loved me, who supported me, who understood me, an older brother and an older sister who kept me in line, and continue to love me and support me. I talk with my siblings every week to this day on, over the internet. But I'm convinced when things work right that you spend your adult life living off the dreams that you had when you were 10. And so it's really important that 10-year-olds have the chance to dream and to play and to find out what's the play that they like to do. And I remember being a kid, I had blocks and I liked to build blocks, but one of the things I built was an altar so I could play being priest. And yet I also had a chemistry set, and I loved fiddling in the chemistry set. And I had a little telescope, and I loved looking at the telescope. And now I get to do all of that. And what's more, I had a typewriter that my dad gave me, which allowed me to, write things up, and now I get to write about the fun I have doing all of these things. There are too many kids who don't have a chance to dream and to play and to waste time, to daydream. I mean, maybe they're over-programmed. Maybe they don't even... The worst thing is when you're 25 or 30 and you've got all of your education behind you and you've got a job and you've got money in the bank and you don't have responsibilities and you can do anything in the world you want to do and you've lost sight of what was it that I wanted to do. But that happens more often than you would think. I think nowadays being in your 20s and early 30s is the toughest time of life, because that's when the program has been finished and everything that you've been programmed to do has been done, and now you got to figure it out on your own. Just as the hardest part of it, being a scientist, is figuring out what's project you're going to work on. It's no longer what your advisor handed you. You've got to come up with something on your own. Something that's so interesting that you will get up on Thursday and go into the lab. And that's hard to do. That's where you have to really be able to listen to that call. That's where going on retreats and having a spiritual life and a prayer life is essential. Because where else do you have the time to shut everything else out and, give God some room to talk to you?
Really appreciate your talk. Thank you very much. I do have a question. You've mentioned this student who found conflict with geology and his maybe family's belief. And so the question is, how does the general relativity Big Bang theory fit with the 6 days creation theory? Can you say a little bit about that?
Sure.
I know it's a big topic.
Totally different talk, but I happen to be prepared. Funny you should ask. You know, of course, that the Big Bang Theory was devised by a priest, Father Georges Lemaitre, who happened to have 2 doctorates, one from MIT and one from Louvain. And he was the kind of guy who could read mathematics the way that you and I could read poetry. And he read the mathematics of Einstein's general relativity and said, oh, this means the universe could be expanding. And if the universe was expanding, and then maybe it came from something when it hadn't expanded, and onward to the Big Bang. Genesis 1, up through the beginning of chapter 2, the 7 days of creation, was written by Jewish scholars during the Babylonian captivity. And you can tell that from the internal language. A lot of the words they use are Babylonian words. And you can tell because the science behind it, the cosmology behind it, is Babylonian cosmology, which was the best science of its day, 600 BC. But the Babylonian creation story said that the world started in chaos, and the gods were fighting each other, and this terrible dragon came, and somebody killed the dragon, and the shell of the dragon became the creation that we're in. And by accident, people were made, but we clever people have finally gotten together and fooled those gods because we made something that is the pinnacle of human creation, the city of Babylon. And the Jewish scholars said, no, we'll take that cosmology, but here's what's new and different and important. First of all, there's only one God. God's already there in the beginning. In the beginning, God said, God's already there. God's not part of creation. God is supernatural. That's what supernatural means, not cast with a flying ghost. God deliberately chose to create. It didn't happen by accident. God says there are no nature gods doing things. There's just me and the laws I've set up, and nature is as logical as day follows night. And God at the end says, and the most important thing is not the city of Babylon, but the chance to have a Sabbath, where we can appreciate what this is all about. Those truths about God are true regardless of what cosmology you have. Whether it's the cosmology of the Babylonians or the cosmology 200 years later, the ancient Greeks, which was the cosmology around at the time of Jesus, or the cosmology that St. Augustine talks about, where he says in his book on the literal reading of Genesis, don't try to turn Genesis into a science book, because it makes Genesis look stupid, and then nobody will see the truths it's trying to teach us. There are 4 or 5 or 6 different places in Scripture where we hear about the creation, not just Genesis 1. And the details of the story are different because the details of the story don't matter. What does matter is the constant theme, the one God who was outside of nature, who deliberately made nature, who saw that it was good, and wants this to be a place where his creatures, us, can encounter him. The last and most spectacular bit of cosmology in Scripture is in the book of Maccabees, 2nd Maccabees. And it's about a mom whose kids are being tortured by Antiochus. And the youngest is about to be thrown in the fire, and she says, don't worry, the God who created this universe out of nothing can take care of you. Creation out of nothing. Even the Big Bang isn't creation out of nothing. It's the creation of the physics that allows the Big Bang to happen. And it comes to us not from some great philosopher, but from a mom whose name we never even learn. So Genesis 1 gives us the courage to do science. It says things don't happen because of nature gods, so let's figure out why they do happen. It says the universe is so good that it's worth studying, not something evil that's going to lure us away from God. It's the cornerstone for why we do science. And that's why it's in our Scripture. Somebody once asked me, so why didn't God just, and instead of telling us this fairy tale, why didn't he just tell us about the Big Bang? And I said, well, if God had told us about the Big Bang 100 years ago, nobody would have known what he was talking about. And 100 years from now, people would laugh because what we're thinking now is probably going to look very primitive in 100 years if we do our job right. The only language that stays eternal is the language of poetry. So that's why we have to have Scripture written in poetry. You see, I told you I had that one ready.
Can you stand up, Steven?
What are some of the habits and rhythms that you have for taking time to admire God's creation? How do you keep the reason for why you do science, particularly when life can be really stressful or busy at times?
I'm really lucky that I'm an astronomer, because when it all gets to be too much, which is a lot of times, I can walk outside at night and look up at the sky. And then I remember what it's all about. Because that Jupiter that I'm trying to describe on my computer model is that dot of light up there. And that's pretty spectacular. And everybody, I think, has to have something like that that gave them joy in the first place. These pictures. For me, that's what does it. People in other fields, maybe, if you're working in medicine, it's to step away from the microscope and see the people who you're curing, see the people in the hospital. Maybe it's when you're a teacher and you see that look, like this look I saw on the student who went, oh my God, it's a wave. I remember right after 9/11, I was in Rome, I was in Castel Gandolfo, and Castel Gandolfo was built on the lip of a volcano. And there will be people who would hang glide, and it's beautiful because there's the right wind currents. And I'm feeling miserable and depressed, and the world is terrible, and then I saw hang gliders, and I go, there's still joy in the world. I'd be too scared to hang glide, but thank you, those of you who are brave enough to do it, to remind me that there's beauty in the world. That's why we have music, that's why we have art, that's why I have my favorite science fiction books that I go back to, when I need a comfort read. But for me, it's looking at the sky. Every day as a Jesuit, I'm expected to spend an hour in prayer. And what I try to do when I'm in Rome especially is to do that during a walk, to go walking through the gardens. So, certainly prayer is essential for that. Does nobody over here ask questions?
Look at that.
Okay, anyway, yes.
Thank you for your talk. I have a question. I've heard at some points in my life about ancient and medieval theologians and philosophers who thought that when God made the world, the laws of physics and stuff, that each law of physics was entrusted to different ministering spirits, different angels that were in charge of gravity and light and so on. And I was just curious because so much modern science tends to think of it as a dead thing, a machine with dead reactions. That's not the impression I get by the way that your presentation talked about science and the joy of it, but I was curious about whether you'd encountered that philosophy and what you would have to say about it.
Not precisely like that, but kind of close to it. You actually find it in a few places in the letters of St. Paul, where he is warning people against that. The world to the ancients was that, the planets were moving. Well, things move up and down because they fall to their natural place, but if things move back and forth, they must be alive. That's why they thought that the wind was alive. That's why the word for breath and the word for spirit and the word for soul, anime, is the same as the word for wind. And they thought that there were, intelligent creatures that made the planets move, and that they would talk to each other, which is, where a lot of astrology got its ideas from. And St. Paul is not saying that that's not true. He says, don't trust in that. The mediator between us and God is not these different spirits, but it's Jesus. Of course, they didn't listen to him. And the medieval theology put the 7 planets into the 7 ranks of angels, and they just tried to Christianize this pagan theology, which eventually we found was kind of inadequate. But the other half of it is I get frustrated when people tell me that life is just chemistry. And it's not because life isn't chemistry, but there's nothing just about it. There's nothing mere about it. It's incredibly fantastic chemistry. It's the kind of chemistry that makes you go, oh my God, it is so cool the way it all works. And, someone who thinks they're an atheist, but loves the truth that they're discovering in science, they're not an atheist. I mean, the God they don't believe in is probably a God that I don't believe in either. Because there's lots of gods out there that I don't believe in. I only believe in one God. And that's why, in some ways, I feel closer to them than I feel to people who say that, you know, God's got everything on a string and it was all preordained and there's no freedom, or that, you know, there's the saved and the unsaved, and now I'm getting into dangerous waters of theology. Because it is this marvelous tension that God gives us freedom but also calls us. It's part of the puzzle. It's part of the fun. When you go, oh my God, this is what I was supposed to be doing. Oh my God, this was who I was supposed to marry, or whatever. That's part of the fun of it. And there's nothing mere, nothing just. It is really cool stuff. It gives you joy, and joy means that God is present. Anybody over here?
Okay, last question over here.
Right.
Andrew, you can decide who.
Thank you. You mentioned briefly light pollution some time back, and that's probably not the only issue that bothers you. And certainly we enjoy the fun of our science and our skill. I'm wondering if issues have led you into the difficult part of politics and putting your shoulder, or do you leave that to other people? Or is that kind of a downside of your work? I'm curious to have you talk about that angle.
There was a Jesuit scientist in our group 30 years ago who would, before dinner, we'd all sit around and have drinks. And he was overlooking Lake Albano. And before we go into dinner, he'd raise his glass and he'd say, "Thank God there's no politics in the Roman Catholic Church." Which he could just say the same thing about science. I've been caught up in the politics of the science. I've seen actually less of the politics in the church. As it happens, right now, the Vatican Observatory is part of the Vatican City-State, and the people running the Vatican City-State are actually really good people. And I know that's not always been the case. We happen to be pretty lucky right now, pretty fortunate. Part of it is, old age. What are they going to do to me? I'm already 70. I want to retire. If they want to kick me out, that'd be thank you. But the worst politics happened to me in science when I was in my late 20s. One of the reasons I went into Peace Corps, besides the story, it was also a big political blow-up. And I remember once walking down the streets of Nairobi, thinking about all those terrible people and how they were trying to thwart me, and then realizing, wait a minute, I'm in Africa, and the city is fantastic, and the sun is shining, and there's a coffee shop with the best coffee in the world. The best revenge is being happy. And that attitude, I think, has allowed me to let go of a lot of the politics that otherwise could drive you nuts. When I got to the Vatican Observatory and I was given the freedom, my instructions from the director then, do good science. And I had the freedom to choose whatever field of science I could choose. I went into one project I'd worked on, and I discovered that most of the people there were nasty people, and they were nasty to each other. And I said, I don't need this. I don't have to do this science. I've got another project I can do instead. One where there's people I like, and I'm really looking forward to seeing them at the next meeting. That's how I chose the science I wanted to do. I had the enormous freedom to be able to do that, thanks to being at the Vatican Observatory. But I think we forget that most of us have the freedom to walk away from a terrible situation and trust that there's something better out there. Not always as easy as it was for me. Because also, there is tedium in science, there is pain in science, there is loss. It's human. It wouldn't be worth anything if it wasn't. and if it didn't have that. The goal is to never lose sight of why you're doing it, where the joy is, where you can find God. And then once you can hold on to that, the rest can, roll off your back. It's the best answer I have. Thank you all for coming. And don't leave quite yet. We've got a few last words. We'll talk about pushing back.
Thank you. Thank you, Brother Guy, for a wonderful lecture. So, as we draw this evening to a close, I just want to mention a couple of things. In the back, we have a couple of tables. We have an Ansem House table where you can gather more information about what we do, upcoming events, or sign up for our emails if you want to know what programming we're putting on. There's also a table from the Vatican Observatory Foundation and a wonderful gentleman named Chris Kennedy back there willing to answer questions and give you more information. So I encourage you to go back there and say hi. And then just to reiterate, our invitation to a reception just across the street. So you see our building and you can see, actually I can't see the Melrose sign from here because the bar on the window is blocking it, but I'm hoping it's lit up. It's a very short walk. Come over, have some nice refreshments, continue the conversation, maybe ask some more questions of Brother Guy. We'd love to have you. We'll have some Ansem House staff at the doors and along the pathway to help guide you if you're a little unsure of where you're going. I think that's all that I needed to say to end the evening. So one more round of applause for Brother Guy. Have a wonderful night.
Nope, I'm set.
No, maybe you did.
I did,
Okay,
up here, yeah.
Good.
That's theirs, this is mine.